Okay, Atash, thanks for providing your working. So I think I understand that where the problem is for you. I think you've got you haven't understood the difference between the photoelectric effect and the difference between energy transitions. Okay, let me talk about energy transitions first. So what you've basically got is, here's your nucleus. You've got different orbits. Remember, it's orbits under Bohr. Okay, so that's n equal to 1, n equal to 2, n equal to 3, and so on and so forth. N equal to 4, and then 5, and then 6. Okay, so what the question is saying is that if an electron goes from this energy level to this energy level, then what should be the wavelength of the photon that it will absorb, okay, to be able to make this transition? Alright, so what's happening? This is an energy level, okay, when it's in the n equal to 3, and this is given by E3 equals minus RH, yeah, z square by n square. In this case, n equals 3, z equals 1 because it's a hydrogen atom, so you have E3 equals minus RH times divided by 3 square. Okay, this is what you've got as your starting energy. It absorbs energy from a photon and goes up to the 6th energy level. What's the energy at that level? E6 is going to be equal to, again, minus RH divided by 6 squared this time. Okay, so how much energy has it needed to go from here to here? It's really the difference between E3 minus E6, right? E3 minus E6, or the other way around actually, E6 minus E3, yeah? Sorry, so that should be E6 minus E3, and that's going to be equal to essentially RH times 1 divided by 3 squared minus 1 divided by 6 squared. This is the energy that it needs, yeah? This energy is being supplied by a photon, so this, let's call it delta E, and delta E equals h nu is equal to hc by lambda. Okay, so you know delta E, which you've computed from this equation. You know h, Planck's constant. You know c, you're being asked to find lambda. Okay, so that's the problem itself. However, what you seem to be confusing with is the photoelectric effect. In the photoelectric effect, yeah, first of all, it has to do with any metal. It doesn't really talk about hydrogen. What you're doing is, here's the nucleus and here's the outermost electron, okay, outermost, and there's lots more electrons in between here. You're supplying it with enough energy and knocking it out completely, okay, so that it's no longer in any orbit of the original atom itself. It's free. So this energy that comes in from the photoelectric effect, some of it goes in pulling it away from the influence of this positive charged nucleus. Yeah, the electron's negatively charged, nucleus is positively charged. Some energy goes in this, that's the ionization energy. The rest goes in providing this electron that gets thrown out, kinetic energy. Okay, and so these are two different ideas. They're not the same idea. All right, and you shouldn't confuse between the two. So there's no need to discount any energy in this case. All right, it's just simple logic. Let me know if there's still a problem.